So let's look more at what's happening during the changes in membrane potential. We're going to start with a graded potential, really a graded depolarization, because we want this graded potential to be excitation. So with a graded depolarization, the inside of the membrane will gradually and locally become less negative. We've seen this before with the junctional folds of the sarcolemma when we're stimulating skeletal muscle. We're going to see this less negative response be as a result of the opening of sodium ligand-gated channels. So what will happen at, say, the dendrites of a neuron is a channel will open once a neurotransmitter binds to it. If that channel is a sodium ligand-gated channel, once it opens, it will allow sodium to influx or enter. That will add a lot of a positive charge, because sodium is a cation and has that positive charge, into the intracellular space of the neuron. That will shift the membrane potential from being very negative, closer to, say, negative 70, to something closer to negative 55 or negative 50. That will be a membrane shift that is enough to be a true spark for an action potential. It will allow us to reach what we have to, which is called a threshold, which is a shift from that negative potential to something much less negative. Now, the next step is actually the first part of the action potential, and it's going to be the initial excitation or depolarization that starts at the axon hillock and then starts to proceed down the rest of the axon. This is going to be a rapid cellular depolarization in response to the opening of progressive numbers of sodium voltage-gated channels. And it only occurs when the membrane potential reaches either negative 55 or 50 millivolts, that's threshold. But it'll rapidly continue until the membrane potential shift climbs to about positive 30 millivolts, or a shift in membrane potential of about 100 millivolts. So that's our initial depolarization or excitation that belongs to the action potential. The next step is going to be the closing of those sodium voltage-gated channels in the axon and the opening of the potassium voltage-gated channels in the axon. That's because we now need to reset the membrane. Keep in mind this is happening segment by segment and very quickly. Once the sodium voltage-gated channels close, we no longer have sodium influx, and instead we'll have potassium efflux or exiting. Now the neuron is going to be losing a lot of positive charge from that intracellular space. And this is going to occur while the membrane potential falls from that high positive 30 back down closer to negative 70. So we're going to start to restore that resting electrical condition of the neuron. But we're not quite going to restore the true ionic conditions. Instead, to restore the true ionic conditions, we're going to see a next step called hyperpolarization that occurs anytime the inside of the membrane becomes more negative than its normal resting potential. So if we started at negative 70, if we have the loss of a lot of cations in the form of potassium to the extent that the inside or intracellular space of the membrane gets more negative than negative 70, then that is a hyperpolarization. It's an inhibitory signal. This is usually due to the potassium voltage-gated channels being slow closers. The longer they stay open, the more potassium is allowed out, and the neuron becomes pretty insensitive to stimulus and depolarization during that time. It's called a refractory period. And then it's due to the sodium-potassium pump, or sodium-potassium ATPase, that the ionic redistribution is reestablished, where we get more sodium outside and more potassium inside, and that's because that's what this pump does, is it pumps sodium out and potassium in to the neuron. So we need all of these components in order to change membrane potential and initiate not only a graded potential, but a true action potential. Keep in mind that action potentials are very brief. They're a reversal of 100 millivolts, and they're all or none phenomenon. They either happen or they don't, and it only is caused when a local depolarization or a graded depolarization, so a graded potential that's excitation, reaches threshold. That's when you'll get an action potential. Those graded potentials are needed for an action potential, but they belong to different parts of the neuron. But once we have an action potential, they're very quickly able to spread through the entirety of the axon and down to the axon terminals. The action potential itself doesn't decrease in strength. Instead, to show an increase in signaling by graded potentials, you would see an increase in frequency of action potentials, but never an increase in their strength. Again, they're always a brief reversal of membrane potential with a total amplitude of 100 millivolts. and they're our primary means of neural communication. Because as we reach the axon terminal, we'll stimulate the axon terminals to release their neurotransmitters. Those neurotransmitters will travel across synaptic clefts and hopefully bind to other ligand-gated channels and initiate their own nerve impulse that may become an action potential. So let's look at this information in a chart like this. So we have a couple of steps labeled. We have 1, 2, 3, 4, and then back to 1. So 1 is resting membrane potential. It's when all of the voltage-gated channels are closed. You might have some leakage channels open, and we've yet to open ligand-gated channels. We might do so very shortly after step 1, when a graded potential reaches the dendrites of a neuron. If that spark allows a shift away from -70 up towards -55 because of an influx of sodium ions at one local space, then we might reach threshold, and that will initiate the opening of voltage-gated sodium channels, which allow even more sodium into the cell, especially along the axon. That will cause a membrane potential shift from -55 up to +30. And that's when the sodium gates will close, because the signal will be traveling away from the initial segment of the axon to further segments and closer to the axon terminals. Then that segment that was initially depolarized will reset. It closes those voltage-gated sodium channels, opens the voltage-gated potassium channels, and we see an efflux or exiting of potassium, and that membrane starts to go back down to an intracellular negative. Because the voltage-gated potassium channels are slow closers, we'll actually go a little bit past not only threshold, but also resting membrane potential, and this will be an inhibitory refractory period called hyperpolarization. But then those potassium channels will close, and we'll return back to our at-rest state thanks to our sodium-potassium pump. You can also see not only a blue line in this image, you can also see a green and a yellow line. These represent the permeability of the neuron membrane to sodium in yellow, and then potassium in green. Note that the permeability of the neuron membrane to sodium increases when the voltage-gated sodium channels open, and it starts to fall when the voltage-gated sodium channels close. And the same thing for potassium. When the potassium gates open, we see an increase in the green line, or permeability for potassium of the neuronal membrane, and then it starts to fall when the potassium voltage-gated channels close. So that's what we're looking at for the generation of an action potential. And these steps would happen over and over again as the membrane potential shifts. What we're going to see essentially is this depolarization, repolarization, and hyperpolarization down each segment of the neuronal membrane. So it's not the entire axon that's going to depolarize and then repolarize and then hyperpolarize. No, it's going to be the initial segment of the axon hillock will depolarize. And then the signal will travel to the next segment, closer to the axon terminals, and it'll depolarize. The reason the signal travels closer to the axon terminal and not backward to the cell body is because that initial segment will begin repolarizing. And then that signal in the second segment that's depolarizing will travel to the third segment and depolarize. And while that segment before the third will be repolarizing, that first segment will be at rest in that refractory period. So each segment of the axon goes through depolarization, repolarization, and then hyperpolarization to at rest. And that allows the signal to travel from left to right in these images, but is really from axon hillock towards the axon terminals. So the direction of travel for an action potential is always towards the axon terminals, because in response to a signal, the soma end of the axon becomes depolarized, and that depolarization spreads down the axon. Meanwhile, the first part of the membrane repolarizes, and because the sodium channels are inactivated and additional potassium channels have opened, then the membrane cannot depolarize again. So the action potential just continues to travel down the axon, always towards the axon terminals. Now, a video that I recommend watching is the ANP Flicks video on neurophysiology, specifically looking at the generation of an action potential. This should be able to be found either on YouTube, and it is also still available in your Pearson software. Another video is propagation of an action potential. It's also an AMP Flex video, again, probably still on YouTube, and then it can be found in your Pearson software. All right, we're going to finish up with talking about coding for stimulus intensity, and that is just talking about how all action potentials are alike. They're always a reversal of 100 millivolts, and they're independent of each other. So strong stimuli can generate more action potentials, but it won't change the strength of the action potentials. Because if a stimulus is still too weak, then it may not even generate an action potential. Strong stimuli just generate more, so frequency of action potentials is how we denote stimulus intensity. So to say that a different way, stimulus intensity is coded for by the number of impulses per second, or by the frequency of action potentials, rather than an increase in strength. You've seen this image before when we were reviewing and looking at information related to the neuromuscular junction and that kind of first introduction to action potentials. Here we have 3 stimuli in purple. Note the one that doesn't reach threshold on the far left initiates or causes no action potentials, whereas the one in the middle, which is slightly stronger and reaches threshold, causes 4 action potentials, and the strongest stimulus is going to cause the most action potentials, because stimulus strength is dictated by action potentials in increased frequency. All right, in the next video, we're going to be looking at absolute and also the relative refractory period. These are going to be periods of time when action potentials cannot reoccur or cannot reoccur without a really strong stimulus. So come back to that video.